Right, let's move on to the slides I prepared. Now we've talked about it a bit, we can kind of get into the problem and we can get into some equations that we're going to use to solve it. But first, we're going to look at this lovely picture, which is of the competition. You can see all the nice cannons. People have spent lots of time creating a lovely cannon just to shoot a pumpkin. Amazing, isn't it? I spend my time doing that. I'm sure you would as well. So, how much does a pumpkin weigh? This is a very contested issue. People disagree on this quite a bit. So I did a lot of research, and it seemed that 20 pounds is a good guess, but 20 pounds is approximately 9 kilos. But I had a brainwave. As soon as I found this figure, I thought, oh, I've got a pumpkin. I've got a way to measure this pumpkin, and why don't I just use this? So we're not going to use 9 kilos, we're going to use 1.7 kilos because this is how heavy this pumpkin is. Hey. And it has a radius that way of about 10 centimeters as well. You'll see why that's useful later. So also we're going to note that we're going to use SI units, so kilograms, meters, seconds, etc. We're not going to be bothering with feet, inches, pounds, all these American measurements. They just don't work as nice when we talk about physics or mathematics or whatever you want to say. So next, drag. Drag is half times density times speed squared times area times sigma. If you've never heard of drag before, drag is the force that carries things back when they're moving through the air. If you flap your hand through the air, you can feel a certain level of resistance. That is due to drag. Drag is kind of air resistance. It's the backward force when we're talking about terminal velocity earlier. And you calculate it by taking the density of the fluid it's moving through, this time air, so it's 1.225 kilograms per meter cubed, times speed squared, which is meters per second, area, which is meters squared, but area, cross-sectional area of the object. So this is our object, and I went for the larger area of the two because this is an oval, there's a circle. Also, a circle is easier to calculate than an oval, debatably. So this is the cross-sectional area, which is 10 as a radius, so that's 0.1 meters. So then it's 0.1 squared times pi, which is pi over 100, is the area of this thingamabob pumpkin. That's the word. And we've got squiggly at the end. Squiggly, which is sigma, which is the drag coefficient. And again, I had to do some more research on this. It ranges from about 0.2 to 0.47 for spherical objects, 0.2 being the smoothest object, 0.47 being a very rough object. And I looked at the pumpkin and said, okay, it's decently smooth, it's got a few ridges, so we'll go on the smooth side. So I went for 0.3. I thought that sounded readable, and it's okay to do the calculations with. Terminal velocity. Terminal velocity is the speed at which the pumpkin can't go any faster. So it looks very familiar to our previous equation. You've just done a bit of fiddling and added a few more terms. So it's 2 times mass of the object times the gravitational constant, or the gravitational acceleration, which is 9.81, over density of the fluid it's moving through, times area, times sigma, which is the drag coefficient, which is 0.3, all raised to the power of half, which is the same as doing the square root. So nothing scary here. And calculation time. So I'm going to now do some mathematics in front of you. If you don't like mathematics, you can skip to the next little video thing, I think. And we will talk about the stuff we find. So I'll either see you in a minute or you carry on here. Right. Oops, having a moment.